This is a tutorial on how to solve differential equations in Python. We're going to use the Scipy.integrate package called ODEINT or ODE integrator. And there are three arguments for that. One is our model function. The next one is an initial condition for our states. And then the time where we want to solve. Okay, and then we have an example differential equation where we have the derivative of y with respect to time equals negative constant k times the state y. Now y of t in this case does not mean y times t. Okay, it actually is y as a function of time, and we want to try to solve that where we have time and y of t, and we want to be able to see what that looks like over time. So we want to come up with a numerical solution to integrate this differential equation, and we're going to use the ODEINT package for that. A couple things that we'll need just as we get started is, well, first of all, just import NumPy. That's going to be a base package that we'll use with many different functions. Here is our ODEINT. So you can just copy these lines. And this one, it's from Scipy.integrate, import ODEINT. If you say import Scipy, for example, you would have to do, to use that function, you'd have to use Scipy.integrate.ODEINT. So to shorten that, we're just going to import the ODEINT function. And then we'll also want our matplotlib for plotting. And so we'll import pyplot as plt. Okay, so the very first thing that we want to do is define our function. And here is our model where our function returns the derivative values, dy dt, as we give it different y values and t values. So basically, you can think of the function as a box, and what you put in are different y values and t values, and what you get out are dy dt. And this is what ODEINT is going to need to be able to solve for y of t. And so if you think about this is kind of in simplistic terms, let's say you're going out hiking up a hill, and you want to be able to determine what the shape of that hill is. So let's just say elevation with respect to time that you're hiking, or it could be distance, for example, if you took the derivative with respect to distance. And at a certain point, you can only maybe look straight down, and you look at the slope. Okay, and dy dt right here might be 0. And so you know you're not climbing. But as you come to this point right here, dy dt is going to be positive, and you don't know that there's a big drop off right at that point. You can only look down. And so let's make this a little less steep. Okay, and then at this point you see that dy dt is negative. And so you know it's starting to go down. So that's essentially what this function is doing. It's just trying to map out what is y of t. And it has these inputs right here, y and t. And then we return the derivative value at that y and t. Okay, so we have a couple other things that are required for ODEINT. We have an initial condition as well. Let's give that initial condition of 5. And then we want to define some time points as well. So you can have a third argument to this as well, like 50 time points. We'll have a start, finish, and then the number of time points. Okay, so start, end, and then the number of time points. By default it's 50, but you could put that at 1,000 if you want to be a little bit more smooth, for example. It's just going to take a little bit longer to compute. So linspace has linearly spaced points between the start and the end with the number of time points there. So that's going to go right in here for our third argument. Our second argument is going to be this initial condition. That's going to be 5. You could just put a 5 there if you wanted. And then model right here. You don't have to put quotes around it or anything. It's just the name of that function. Okay, and what's going to be returned is our y value. That's going to be y of t. And then we just simply want to plot it. plt.plot t comma y, or t is our x-axis and y is our y-axis. And then I just put an x label and a y label. And then I show the plot. You don't have to do that in if you're using like a Jupyter notebook. Okay, and there is our plot right there. So I encourage you to go and just make sure this works on your system, that you have Scipy installed correctly, and you can use NumPy as well. Okay, so we can also do things like pass additional arguments into our functions. Like, let's say we don't know the value of k. We had determined that before, but let's say we want to have our function be able to accept different values of k. And so that's going to change our equation slightly. And so the only thing that we need to do differently in this is just put in the new fourth argument, fourth input to our system, where we say args equals k. Now you can't just say args equals k. You have to do this funny thing called a tuple. Okay, where normally if you had k1, k2, k3, so these are the round parentheses here, and you would normally define those as a sequence of inputs. If you only have one of them, then you just have to leave that blank. It's kind of funny notation, but you just leave that blank with a comma there because it's expecting a multiple of values coming in, but you only have one. Okay, in the future you may have multiple, but if you don't, just use this type of syntax. Okay, so we have different values of k, and then we want to record those as y1, y2, and y3. And then we're just going to plot all of those three lines right there, plotting y1, y2, and y3 as a red line, a blue dashed line, and a green dotted line. And I'm also going to put in a label to be able to know which ones those are, and you can make a legend with that. I also like to do sometimes inside that parentheses there, location equals best, and then it'll pick the best location for the legend. Okay, I didn't do that this time, so it's going to default into the upper right corner, which looks like it's okay. Okay, so there's our same solution that we had before, but now k equals 0.1, 0.2, and 0.5, and so you can see that the higher the k value, the more quickly it decays to this value of 0, but all of these would continue on and decay to a value of 0. Okay, so there's our solution with ODEINT. You can solve multiple differential equations at the same time. I'll show you in some of these examples below. Okay, so here's problem 1. We're going to try to integrate this system right here. And so let's go ahead and just start from scratch. Now on the now go ahead and try this yourself, and then if you get stuck, come to the course website and go to the PDC website, and then if you come down here on the right, this is Solve with ODEINT. And here's all the material for that, the exercises that we just went through, and you'll see a little button right here that says Show Solution. Okay, so you can kind of see the here is some of this the source code for this. So very similar to what we've already solved. So I'll click the Get Code, just copy that, and so for this first one, I'm just going to copy that. I'll create a new text document. I'll just call this problem1.py. Okay, Python 3.6, and so let's see if this will run. Okay, let's see if I'm missing any modules here. Okay, so it's going to run and then hopefully show the figure. Okay, so there's the figure right there. I just included, just like we showed before, we had the differential equation. We basically just had to modify this line right here from the prior example, and then maybe also change our final time so we could see the region that we were interested in. So I went from 0 to 5 I solved it with this ODEINT function with model, y naught, and t, and then just plotted it. Okay, just a little bit more complicated. Okay, so I'm going to do a save as, and I'll save this as problem 2. In this time, I'm not going to use the solution. So let's try to work through this together. Okay, so use steps from 0 to 2 at time 10. And the very first thing that we notice over here is that we have a 5, but our function needs to be able to return dy dt. So let's just go ahead and divide both sides by 5, and this is going to then cancel, and we'll have a function of dy dt with initial condition equal to 1. So let's change our initial condition to 1, and then we have minus y plus u, and I'll go ahead and divide by 5 as well. I like to do 5.0 to force it to be a floating point. Now that's not as big of a problem with Python 3.6, but 2.7 it did really funny integer division stuff. Okay, I'm just going to put an if statement here. If t is less than 10, then we're going to say that u is going to be equal to 0, and else u is equal to 2. Make those floating point numbers with the dot 0. Okay, and then I return the dy dt. So I just had to put a little bit of logic in here, an if statement, and so it's going to step from 0 to 2. And let's go a little bit further into the future. I'll go up to 35 and solve this. Okay, here goes problem 2. And there you can see that it started at initial condition 1, was going to decay to a value of 0 like we had seen before, but in that case it changed. You had an input step change to the u value changed to 2 immediately, and this started to come up to that value of 2. Okay, so we had a change in one of our parameters at a certain time. Now because you have t is coming in as an input, we can use that to make decisions about what the value should be at different times. Okay, and don't forget you have to put you have to isolate your derivative on the left hand side of the equation and put all of the terms on the right hand side of the equation. That function needs to be able to return dy dt. Okay, so we've got another one. We've got two differential equations here. So let's see if we can solve those in the same function together. Okay, here's let's save this as problem 3. Okay, and here is let's see. I'm going to just combine these into one value z. I'm going to change that name, and then when it comes in, I'm going to say that x is equal to z 0 and y is equal to z1. So I'm going z is going to be 2 elements, not just a single value, but it's going to be an array of values. And then I'm going to have 2 derivative values as well. So I have dx dt, and that's going to be equal to 3 times, I have to use the numpy or the math function for exp, and that's going to be minus t. And then we have dy dt, and that's going to be 3 minus y of now I don't put y of t, it's just going to be minus y. Okay, whereas the exponent up there is a function of, so that you do put the negative t in there, but here you do not put in like t right there. Okay, it's just going to be y. Okay, and then instead of just returning dy dt, I want to return 2 things. So I'm going to put a list here of things I want to return. So I'm going to return 2 values. And then I have my initial conditions. I'm going to do z, and that's going to be equal to 2 different values, 0 and 0. So this is my x naught and my y naught right there. Okay, and then I'm going to be going up to, let's just go up to 10 in this case. See how that works. And then instead of returning y, I'm going to be returning z. That's a combination of the x's and the y's. And let's just get to that point right there. I'm going to comment out this, and let's just see what it returns. And let's see if I have any errors here, first of all. Okay, and so it finished. Here are all of my z values. Okay, so it looks like they're fairly equivalent, but let's break those into two different vectors here. So I'm going to just take all of my rows, I put my colon there, and I'm going to get just my first column. And that's going to be x, and then y is going to be all of my rows with my second column, which is going to be 1, and then I can plot the results. So let's go ahead and put both of these on to the plot, and so I'm going to have x, and let's go ahead and make that a red line, and let's do our y value and make this a dashed line so we can see what's underneath it. And then I want some labels here as well. And let's see, I'm going to have x of t, comma, y of t. And I think that's right. I'll probably have an error, but we'll fix that as it comes up. Oh, okay, they're very good. So they're equivalent. Oh, you know what? I should have just done something like legend. There we go. I'll do legend instead of y. Let's see if that turns out any better. Okay, so it looks a little bit better. I've got the x of t and the y of t there. Okay, so you can see that those two are equivalent. You can see the values that they went to. This is a demonstration of how to put in, solve multiple differential equations together, and then we basically just have to combine the initial conditions and define our time points the same way, and then what gets returned is just two column vectors, or multiple columns of values that are basically the x of t and y of t, and then I'm just separating those out and then plotting those two. Okay, so I had two. Let's go on to the final one now. Here's one where we have a step input change, but we also have two differential equations. So not very different from what we just solved. Don't forget to move the 2 and the 5 to the other side of the equation. Okay, and then we have a step function change from 0 to 2 at time equals 5. So s of t is just this step function that changes from 0 to 1 at time equals 5, but when you multiply it by 2, then when you multiply this by 2, then it's going to go to a it's just basically a step of 2. Okay, and then we have these initial conditions right here as well. So let's just modify this script. It's pretty close to what we need already, but I should probably save this as problem 4. Okay, let's save this as problem 4, and then go into this. We have equals negative x plus u, okay, divided by 2, and then this one is going to be negative y plus x divided by 5. Okay, so I've got my function defined, and then I want to put in, let's say, the value of u right there, and let's have that be an input. We'll define the u value outside of this. Okay, so I'm going to have, let's do 100 points, and I'll just say n equals 100 because we're going to use n later as well. 100 points. And then I need to create some new vectors here. I have my initial condition already, and those are going to be 0, 0 like we had before. But now I want to create a new u value, and so I'll just say numpy zeros, and I'll say that's going to be 100 zeros. Okay, so just a list of 100 zeros, but I want to change that at time equals 5. Okay, so there's about 10 points per, let's see, let's go out to, I'm going to go out to 150, maybe do out to 15 time, and then it'll have 150 time points. And so each one is still going to, each time period, 1 second for example, is going to be 10 points. And so we want to change u after t equals 5, so that's going to be 51. Okay, 51 on is going to be equal to 2. Okay, so I've set up my input, my u value, I have my time, and I have the number of time points. Now let me go ahead and set up x as well, and I'll just say that is going to be zeros n, and y is zeros n. And so instead of just solving the ODE in one time step, I'm going to set up a loop for I in range n. And I'm going to go from 1 to n because I have the initial conditions already that are equal to 0. Okay, so I don't need to solve for time step 0 because those are already defined as zeros. And then as I go through this, I'm going to have an argument that is going to be my ui value. Okay, and I'm going to just integrate it one time step. So I need to set up a time span is going to be equal to t I, let's see if I can get this right, I minus 1 to ti. So I'll show you these vectors as we go through it just so you can see. But basically I'm just taking one time step at a time. I'm going to integrate it, and that allows me to have different inputs at every time step. Okay, and then after I finish that integration, I want to get my new initial condition for the next time it loops through that. And so I'm just going to take the endpoint, so I can do that with z negative 1, but I know there's only 2 steps here because I defined it as here's my starting point that I want a value for, and here's my ending point. So I'm just going to take the second time point, second row in that z solution, and so that's just going to be z1. And then I want to, instead of defining all of my x's all at once, I'm just going to say that xi, let's see if I can do this, xi is equal to z naught, and I'm going to have that be the first element of z naught, and then yi equals z naught, and that's the second element of z naught. So I'm just going to record those, and then we'll plot them. And let's also include a plot of u in there, and we will do that as a black dotted line. Okay, and I'll just include that here, u of t. Okay, and I think that should be about it. So let's go ahead and simulate this and just see what it does. I'll break it down into a couple more steps for you in case you didn't pick up on some of that. I'll also try to work through any errors that came up in the process. Okay, so it's going to simulate it, and you can see u steps up from 0 to 2 at time 5, and then you can see the value of x and also the value of y as we're integrating those. And so what we may want to do is just come in here and show a couple of the, when I run it again, I'll go ahead and close the plot, and then let's go back to the command line and see some of these values. Okay, so the very last time it ran through that loop, there was the time span. It went from 14.9 to 15. Okay, so that was the very last one that it did. So it integrated up to 15, but that was the last time segment. Okay, z naught it said that there's my value of x and my value of y. That's my initial condition. If I were to loop through one more time, it would have used those as the z0 initial condition. So what I'm doing is looking at values after it finished all of these loops that it went through in range 1 to 150, and it integrated and stored all those values in x and y. Okay, so here's x right here. You can just see it's a list of values. It was 0 before that step change happened, and then also y. Okay, so y, let me make this just a little bit small, move it up so I can see it. Okay, and then y is going to be, let me do a print on y, and I'll just print from 0 to 10, and those should all be zeros. But if I do print y from 120 to 130, I'm going to see those values were changing as every time it looped through, it got an additional value of y in that list. Okay, so showed a couple of other things. It's probably the most complex example that we've covered so far. We broke this down into a loop and just integrated for one time step at a time as we went through this. There's our integration with this optional argument u. And then we had our initial condition z0 that we defined here, and that was going to be plugged back in here as our initial condition, and then it'll compute a new z value. But before we erase that z0 value or change it again, we need to record those so that we could plot them down here as x and y. Okay, so there is our final example, just a little bit more complicated on problem 4. And then what we'll do is we'll give you as a homework problem, as this is the challenge problem then, is to simulate HIV. Now this is a human immunodeficiency virus, HIV, that can develop into acquired immunodeficiency syndrome or AIDS. And fortunately there's a lot of very good antiretroviral drugs that can prevent this transition and allow patients to lead healthy life. Here are some initial conditions for our states, and then you have 3 equations. So what you're going to try to do is integrate these, just like we did the 2 equations. You're going to have a 3rd equation now, and you're going to have some parameters here, the KR1 through KR6. And this might be a patient's, some data for a patient not treated with antiretrovirals over the course of 15 years. You can see maybe some data points on how the virus spreads through the body, transitions to AIDS. So I want you to try to simulate these 3 differential equations with these parameters and see if you can come up with a plot that looks similar to this. Make sure you plot it on a semi-log y plot. So you may need to do an internet search to figure out how to do that. Okay, here's a couple references as well with a couple links. But you should have enough information on how to set up and solve multiple differential equations that are solved together.